So IR gives functional groups and mass spec gives mass. You have an unknown compound, be interesting or important to know what's the mass of this molecule, of this compound. Assuming it's pure, what's the molecular weight? Well, mass spec provides a molecular weight. As long as you can interpret it and get that information and know what you're looking for. Document camera. Okay, resonance. Does resonance seem to be an important topic?
Yes.
Yes, resonance is an extremely important topic. And it can influence the outcome. The Regio selectivity of reactions, outcome of reactions. React this alkene with HBr, do a hydrohalogenation reaction. And product. The question is really where are you going to form carbocation? Because where you form that is where the bromide is going to be affected. Top or bottom? It will be bottom. And if you drew both carbocations, which I should have drawn, we can get H here. Okay? We attack H, leave cation up top, or we could attack the other way. I won't show mechanism. We could attack and put H up here and cation at the bottom. This is where the electrons move away from the bottom carbon, go attack H, leave carbocation down here. Look familiar? Okay, the question is really which carbocation is the most stable. It has two potential pathways to go. Which way is it going to go? This one. Why, Amelia? Closer to. Okay, hopefully what you're trying to say is we can do a resonance structure here. These electrons can move in there, and that would give what? Double-headed resonance arrow. Okay. There was resonance on the top mechanism on the test. Okay. You should have used a resonance arrow to go between structures. I did not count off if you did not, because we're sort of in the process of working with resonance. In the future, though, you will be counted off if you do not use vertical arrows. Okay. Double-headed resonance arrow. I'm showing a resonance structure going between resonance structures, and that would be double bond here. What does this arrow mean to you? Moving in to make a pi bond. There it is. There's still a new H there. And of course, all resonance structures have same net charge. Golden rules. Where's the positive now? Now it's on nitrogen. I need to show our charges right next to the atom. I know in Gen Chem you put it way out there in outer space. For me and for organic and for most, you want to put the charge right on the charged atom. As much as possible to clearly stain. Okay? Is this resonance stabilized? Can you draw a resonance structure here? What if I do this? Now that's going to make a sigma. That's going to be a sigma bond, a single bond. It's also quite strange. I don't know if they can do that. We're talking about theory. Resonance, there's a lot of theory there. That is, that's an empty p orbital. What type of orbital is a lone pair in? P orbital, because anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. You got two p orbitals here. They're conjugating. That's what I'm trying to show here with my resonance. Okay? That's an empty p orbital. Is there a p orbital? Is there a p orbital anywhere else? No. Is this lone pair in a p orbital?
No, it's not.
No. Why would it be? Is this lone pair next to a p orbital?
No.
No p orbital there. No. That lone pair is in an sp3. And since it's not in a p orbital, are you going to do any resonance with that lone pair? No. Golden rules of resonance. You only move pi electrons. We only do resonance with electrons that are in p orbitals. Okay? So all that theory is there. There's no resonance here. It's a localized carbocation. This one's delocalized. The charge is neither fully on carbon or nitrogen. It's spread over between them both. If you look at the hybrid, okay, does the hybrid look more like left or right? Which one's major? there, more bonds. All atoms have octets. See over here, the carbocation does not have an octet. But over here, the nitrogen does have an octet. 2, 4, 6, 8. Again, golden rules of resonance. If a nitrogen or fluorine or something like that, as long as this has an octet, it doesn't mind taking on a positive charge. Okay? So that's at least 3 topics from the golden rules page. The remaining topics are also important. So, this is the carbocation it's going to form, and then the bromide attacks here. Okay? You can either attack right there, you can work with any resonance structure. If you want to work with this one, you take these electrons and you add them here and you push these back over. What does that arrow movement give right there? It gives this. And the lone pair is back on nitrogen because it got pushed back over right here. All right? So next time you're out, having lunch with friends and you talk about resonance and someone says, well, you don't have to work with that resonance structure. You tell them, no, you can work with any resonance structure. And you remind them that they're all fake. So why do I have to work with that when I can't work with this one? What you really are working with is the hybrid. This is really one compound, right? But again, the hybrid has these partial bonds. Kind of hard to do mechanisms with partial bonds. So we work with these structures. Okay, enough of that. Anybody got the next one? Which one's going to be formed? Yeah, the first one, the bringing the cation, left or right?
Left.
Left, correct. Why? It'd be resonance stabilized. What type of cation are you going to make up here? Name of it.
Carbocation. Positive carbocation on secondary.
What's the name of that carbocation you're going to make up there?
A benzylic cation. A benzylic cation. A benzylic cation?
Yeah, you're going to make a benzylic carbocation. Yes. Yes, benzylic carbocation is quite stable. And then the iodine is going to attack the benzylic carbocation to give them product. And fast step. So forming the carbocation is the slow step, right? Okay, stabilization of anions. We looked at cations. Anions. Well, we can start with this. How do you stabilize an anion? You move the electrons towards it or away from it? Away. Okay? I see students all the time try to do resonance like this. I'm like, why are you moving electrons towards that negative site? That's the opposite of where electrons want to go. The opposite of getting towards neutral and more stable. Okay? All right. Let's start with just drawing resonance structures. A lone pair, if it's conjugated, is a great place to start. Is that lone pair conjugated with a double bond? Is a lone pair in a p orbital?
Yes.
Yeah, because anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Well, let's do the theory real quick. Don't we have p orbital here and p orbital here? One electron makes pi bond. See the alkene over there? Sigma bond and pi bond. The lone pair here, what type of orbital is it going to be in?
P orbital.
P orbital. Because haven't we said anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital? All right. Yeah, those are interacting too. This is a pi system consisting of 3 p orbitals. How many electrons in the pi system? 4. Sounds like an extra electron. That's why it's a minus. Okay, here's your theory. Yes, the lone pair is conjugated. Okay, if the lone pair is conjugated, it's a great place to start with resonance. And what we can do is, I call this the old in and out. Okay, move these in. But this has 4 bonds. It can't make 5 bonds, so you got to move the pi bond out. What does that give? Well, we have double bond over there. That's what the first theorem means, right? Electrons are moving in to make pi bond. Pi bond here is moving out to become what? A lone pair on the carbon, and yes, that's now a minus charge out there. Because yes, there's 2 H's here. 2 H's there. If you draw them in, count your charge, you see it's minus. Okay? There's your resonance structure. An alternative fluid structure where we only move pi electrons. Yes. By the way, which is major? Which is better? They're equal contributors. Yes, equal. The child looks exactly like a good blend of mom and dad. That is, what's the bond order between the first 2 carbons over here? Is it double or single? 1.5. How about over here? Is it single or double? 1.5. All right. The bond order is exactly the same. What's the charge of this carbon in the hybrid? Neutral or negative?
Partial negative.
Partial minus over here.
Partial negative.
Partial minus, okay? Which bond is longer? Carbon-carbon over here or carbon-carbon over there?
Same.
They're the same. Because you know that's fate. The true structure's over there. They're the same. If you could see the electrons, you would see that it's very symmetrical. Charge, is the charge sitting on the left carbon or the right one? Partial on both. Equal amount on both. It's a perfect blend. Okay? But the charge here has been delocalized to another atom. And the charge is spread over 2 atoms. And that's good. That's better than it just being on one. So charge delocalization is seen here, this time in anion. And we did it. All right? How about down here? If there was an H here, that would be phenol. This is phenoxide. Have we done that? Phenoxide, have we talked about that before? Okay. What is this? Well, what is just an O minus or O2 minus? Oxide. What if you put an H on it? Hydroxide. Kind of a hydrogen oxide. Hydroxide. Well, what is this? Oxide with a phenyl on, or benzene is called phenyl. Phenoxide. Yes. If it was neutral, it would be phenol. Okay. Can you do resonance with the phenoxide anion? Yes. Lone pair is a great place to start with it. Okay, it's conjugated, yes. Okay. These electrons here go in and out, yeah. Everybody good? What's that? There's 3 of here.
One that was made.
But I moved one in. Exactly. Right. I mean, if you know what you did here, there should only be 2 over here, right? But unfortunately, I see it a good bit where there's an answer with 3 lone pairs. And I'll put a question mark. Okay? Everything comes from your error limit. Okay? Yes. Same net charge, yeah? We're good? Go in and out. Can we draw additional resonance structure? Yes. These electrons can move in here to make pi bond. Now either bond you can consider the pi bond. Okay, I could do that, or I could do this. Yeah? Go in and out. Nothing changed over here. This became pi bond, and this pi bond moved out to become minus here. Yes, it is minus. Nothing changed here. Yeah? And we can go one more time. These electrons can move in here, and these can move out onto the carbon. that right? And then if these move here, what are we going to do? What do you want to do? Move that bond away? Well, the in and out is we're moving, we make pi bond, the pi bond gets moved out. We don't move sigma electrons. So we move this in here, and the pi bond gets moved here. Now what does that do? I'm not going to redraw that, but the charge is now back on what? Back on oxygen. Now the pi bonds will be changed in the ring, but we're back on oxygen, so it's no longer further delocalized. Have I ever told you how they write in medical school on the boards? Whenever I pick up the eraser with my left hand, like this, okay? Because in medical school, they write like this. Okay? Two-handed. All right. So what's a hybrid going to look like? Well, if you look at it, it's partial bond here, partial bond there, partial bond here. It's partial all the way around. How about charges? Partial minus here. Which carbon of the ring has partial minuses? Well, just look at your resonance structure. That tells you. That one there, that one there, and that one there, correct? I mean, there's your hybrid. Are all these equal contributors? No, one is major. Which one's the best? Why the first one? In the ring. Well, it's got the traditional benzene ring, and that can be an argument. But it doesn't have 12 or more bonds. They all have the same number of bonds. The difference, why this one's best, minus on oxygen. They all have octets. They all have the same number of bonds. Minus on oxygen would be better. Isn't the electron density going to sit more on the oxygen? Okay. Ever told you about putting water in a garden hose? It spreads out equally. Okay. Does it always spread out equally? If it's laying flat on the ground, it does. But what if you take the garden hose? Okay, I don't have a big hose, but what if you lifted up the one end? Would the water move somewhere? Where would it go? It would go down. Why? Gravity. Okay? And maybe if the hose was not completely filled, now if the hose is filled, the water has nowhere to go. It's going to remain in there. But if it's partially filled, if you do like this, water is going to run and be cooled down to the bottom. And there will be no water up here at the top of the hose. Well, gravity is analogous here to electronegativity. Are the electrons going to sit all through here, or is the electrons going to gravitate towards the oxygen? They're going to gravitate towards the oxygen. So in the blend, there's actually more electron density towards the oxygen. Just like if you hold the hose, it's going to be more towards the so gravity, electronegativity, sort of analogous in this regard, yeah? But I'm not going to account for that in my blend. I could ask you this. Of the 4 atoms where the charge is delocalized, there's more charge where?
The oxygen.
There's more charge here. Because that's a major resonance structure. It's all these the same thing. And so if charge was some type of color, maybe red, that would be more red here. In a pictogram or something. Okay? So that's the hybrid, yeah? Resonance structures, phenoxide anion. Why is that anion more stable than... I mean, what if there were no pi bonds in the ring? Which anion is more stable?
There's more bonds, so it's more
This one, because the charge is very delocalized. Any resonance here? No, there's no resonance here. There's no p orbital. It's a localized anion. Here we do spread the charge onto carbon. Now carbon doesn't love it, but it's better than nothing. And that's why phenol is more acidic than this alcohol. Because when you consider acidity, don't you look at the conjugate basis? Okay? At this point, aren't I repeating many things we've talked about this morning? Over and over? We're building, because starting week 1, we talk about things and it all comes together. Okay? Which one of these anions, carbanions, is most stable to least stable? Yep. Think about that. So we can stabilize an anion by delocalizing it by resonance. Lone pairs, conjugated lone pairs, great place to start when drawing your resonance structures. Using the old in and out. Electrons in, pi bond out. What about neutral molecules? The first page we started with neutrals. But there was no polarity and there was no lone pair. So it was a little bit difficult. All right? You do resonance here. Well, notice the similarity between this neutral structure and the phenoxide anion. It's going to be the exact same. They're isoelectronic. Okay? It's just because the nitrogen is just neutral here. But it has a lone pair. And that's a great place to start with resonance. Of course, as long as it's conjugated. What type of orbital is that lone pair in? D orbital, right? Is this P orbital next door? Okay. It's conjugated. What can we do? Electrons in, electrons out. Yep. Does it give that? What's the problem?
It should be a positive charge.
To begin, that was a good way to state it, yes. I like how you stated it. Say it again.
There should be a positive charge.
Okay, did everybody hear that? No? Did you hear that? We got some folks who didn't hear. I'm going to ask you to say it again. Because there's a golden rule that says what?
Resonance structures should all have the same charge.
What's the charge of this? Neutral? Then this has to be neutral, is it? No. All of a sudden it became minus. Something's wrong. That's because there's a positive here. And of course, week 1, we can tell that's a positive nitrogen. So both of those have the same net charge. And they're both net neutral. But see the similarities to that up there, and we can draw other resonance structures. Basically, this is an example of what's stated here. Drawing resonance structures of a neutral, but something that has a conjugated lone pair. Great place to start. And then we can keep going. I'm not going to draw the additional 2. It's just analogous to up there. Yeah? Electrons here, pi bond out. Then you can answer questions. Which carbons of the benzene ring of aniline are most electron rich? That's the question we asked for phenoxide here. Basically, look at your resonance structures and where's the electrons going to fall? Which carbons in the benzene ring? One of them is that one. So then there's 2 others. Okay? We can extend this out, and what if we put other groups on the ring? We can do resonance into the ring, sort of around the ring. But can you do resonance of this lone pair into this double bond? In one case you can, in another case you cannot. You need to do this on your own, draw resonance structures, and then ask the question below. The question is a little bit different down here. Which amino group of the 2 compounds above is most electron rich? But these types of questions all come from understanding your resonance structures, drawing them, and then assessing them. And then figure out, what is the question you're really asking me? Okay? And we can look back at those on Wednesday if you want. We were dealing with lone pairs there, neutral compounds with lone pairs. What about neutral compounds like this? And what does it mean to be like this? You draw any resonance of this compound, acetone, wash your glass over. You draw a resonance structure of that. Resonance structure of fossil. Somebody got one? How did you get that? What was your thought process? Only move pi electrons. That's good. It's a good thing to know.
So because we can only move pi electrons, the oxygen wants to take the electrons.
Okay.
And we have to put it at neutral charge. So the oxygen will have 3 pairs of loaded electrons with a negative charge, and the form of carbon.
You got lone pairs there. Aren't lone pairs a great place to start with resonance? You're making good comments over there. I'm just having trouble hearing.
Don't they almost, the lone pairs have to be resonant?
Yes, if you're going to be resonance, electrons need to be in p orbitals. Yes, exactly. And so why do you make that comment? Keep going.
Those lone pairs will be the
Very good. Yes, those lone pairs are not in p orbitals. What type of orbitals are they in? sp2. So don't do any resonance with those. We agree? All right. Good. Those lone pairs are off limits. They're not in p orbitals. No resonance there. So what can you do? All you have is 1 pi bond. 2 pi electrons. What can you do with those electrons?
Should make them lone pairs.
Well, what you can do here is you have a dipole here. Yes. Which can be analogous for gravity. Which way is the electron going to want to flow?
To the oxygen.
Downhill, right? Downhill is like towards oxygen. Yes. What if I just take these and move them up? There's no in and out. It's sort of just out. The oxygen is pulling them out toward. What does that give? One more? Why one more? There's 2 lone pairs here. Oh, I'll move the pi bond out to become a third lone pair. Oh, okay. And charge? Same net charge, net neutral? Okay. Yes. That is coming from polarity, intuitive oxygen pooling. Pi bonds are, which one is more easily polarized, more readily polarized, a sigma bond or a pi bond?
Pi bond.
Why are pi bonds more readily polarized? Pi bonds are weaker. Okay. Pi bonds are more readily polarized due to electronegativity. Okay? That oxygen there can take, here we go, I'm oxygen and you're carbon. We got a sigma bond and a pi bond. But see, what I can do is I can just say, okay, this sigma bond is held tight between us, okay? With the pi bond, I'm going to pull it more. I'm greedy. But this is held tighter. Pi bond is more polarizable. That's what we're illustrating here, doing here. Okay? And that resonance structure over there, which is a resonance structure because it's an alternative Lewis structure, but all we did is we pi electrons. That's very illustrative of the electronegativity, the polarity you have here with acetone. What's the true structure? Somewhere in between. Right? So, is it a single bond or double bond between the C and O? 1.5. Okay? What about charge? Is the oxygen neutral or minus? Partial minus. Carbon, neutral or positive?
Positive.
Okay, there you go. There's how acetone really looks. And doesn't that really show the polarity, how the oxygen has pulled it and it became polarized? So the hybrid really illustrates this nicely. Okay, question?
When we put lone pairs on the hybrid structure.
Hybrid's hard to work with, I typically don't. I mean, you could, some people may. They get a little convoluted. All right, so I didn't put lone pairs there. Can you show resonance structures down here? All possible resonance structures. We have a cation here. Can you show resonance structures with the carbocation? All possible resonance structures. How about that one?
The lone pairs are conjugate. So the lone pairs aren't in the pure orbital, so they can't go and make a pi bond.
Lone pair is not in the pure? Why not? Anytime a lone pair is next to a pure, we're going to want to finish it. Yeah. One lone pair is conjugated. That fluorine is sp2. One lone pair in a pure, two lone pairs in hybrids. Graph it. You knew that 2 months ago. Yeah. Basically, you got an empty p orbital. The lone pair on the fluorine is in a p orbital, and those two p orbitals are interacting. Illustrate that with that big structure over there. Can draw other resonance structures. So I can delocalize it to the F. Any other resonance structure?
Same that we do with us.
What? What you got? Anybody got something drawn? Anybody? Over here? You have a structure drawn?
Yeah.
I can't get back.
Where's it at?
Where it's delocalized around.
That's what I thought you might have. Sorry.
Is that not right?
Not right. Not right, but that's okay. Because wise person once told me that it
Charge is exponential.
will make a lot of mistakes. The more mistakes you can make, the more you're going to learn. Okay? So it's not right, it's a mistake. But let's learn from it. Okay? Because once you do it once, then you usually don't do it again. Problem is, you got to do it once. All right? Don't you agree? If you mess up once, don't you really, then you say, no, I'm not going to do that again. Yeah. So everybody needs to mess up, then you won't do it again. All right? I'm going to erase this so I can start fresh. What is commonly done here is pi bond down. Yeah? We moved pi bonds before. What would that give? Boom, boom, boom. Yeah. Pi bond here. Oxygen, how many lone pairs on oxygen?
Two.
Two here, two here. And positive charge?
Oxygen.
Now here. But what do you think about the oxygen there?
It doesn't have an octet.
It has no octet. And if you look at the golden rule page, it talks about this. We said this. Oxygen, chlorine, fluorine don't mind taking on positive as long as what? As long as they keep their octet. Okay? This oxygen is very bad. It's going to come knocking on your door late at night and make you regret doing this. So while this is officially a resonance structure, it is very bad, and we don't want to show this. Because, think about polarity. This pi bond, which way is the pi bond really moving here? Isn't it going towards oxygen? That's inherent electronegativity. Okay. In the end, there's only one other resonance structure you want to show here. And sometimes in my instructions they'll say, show a resonance structure that is just as good or better than the current. Well, this one's just as good as better because this is actually major, right? Why is that one better than this one? More bonds, etc. Okay. Is this one just as good as that one? No, this one's bad. So for my directions, you're not going to be showing this. And I would tell you, never. Golden rules: never have an oxygen, fluorine, etc. without an octet like this. This is actually partial plus, partial minus over here. Okay, and this right here is actually not great. It's going to be kind of hard to form cation here. We are helped out by this guy who's willing to help, and we show that in this resonance structure. Not that good. Okay. So, ultimately, Christina, you keep octets on oxygen. This is no octet. So, but that's why I have that question, because I want you to see that and make that mistake and learn from it. And each section is trying to illustrate key points. Please read the top if I haven't mentioned a single thing. Okay, let's finish this up. Acid-base chemistry. Please go back and pull that handout out from week 1. Look at the resonance section. Okay. Which is more acidic? Well, phenol, right? 10 versus 16. Why? We answered that earlier today, right? You really want to look at the conjugate bases, correct? The anion here is very delocalized. Like resonance, we drew resonance of phenoxide earlier. Is that oxygen anion delocalized? No, so it's not as stable. Thus, this compound is not as acidic. All right? Why is the carboxylic acid more acidic than phenol? Basically, at this point, I need to ask you to be looking at these types of questions, and we'll look at them after I make sure that you have looked at them. Okay. Down here we have phenol with these nitro groups. You'll see nitro in organic 2. Lewis structure for nitro is nitrogen with double bond to oxygen and single bond to oxygen. This oxygen is charged, that nitrogen is positive. But of course you have resonance of the nitro group itself. This is another example of when we add groups to the benzene ring, can we do resonance into that group or not? And the more resonance you can do, the more delocalized your charge is. Right? So let's, basically there's a few other miscellaneous things here. We're out of time. We'll try to pull this together on Wednesday, see what type of questions you have, and we'll begin the diene chemistry. 1-2 versus 1-4 addition reactions. First half of that handout. The second half of that handout is by video, Dills Alder. Have a great Monday, guys.